Okay. Let me see the video showing up. Oh, yeah. Okay. All right. So let's get started. Okay. So welcome back. I hope you all had a good break. Just as a reminder, we have our exam this week. Okay. It's going to be on Thursday, 7 p.m. in Thompson Hall. And I sent an email about the exam, but looks like the email didn't reach some of you. I don't know what is going on with the mailing list, but I have posted all the instructions on Piazza, and then as an additional measure, I sent it to Canvas. All of you should have received that. The material on the test is from lecture 1 to 12. What is being taught today is not on the midterm, it will be on the final. Okay, so you don't have to worry about it for this week. Okay. The other thing is I gave out a sample exam, that's last year's midterm actually, and some practice problems. Yeah, that should give you some flavor of what types of problems to expect on the test. So we have office hours this week, so if you're reviewing material, have questions, you can come see me. You can write questions on Piazza. We are happy to answer any questions that you have before the exam. Okay, I did set the test already. So I think my estimate is it's somewhat simpler than the sample exam. Okay, but you can tell me after the exam if that's correct or not. All right, so we'll see. Okay, but as I said previously also, the way you want to approach the test is look at the lecture slides first. That's the material that we have actually covered, and that's what you should know. Okay, you can then use the lecture notes, you can use the book to learn more about the material, but you don't have to look at things that we have not covered on the lecture slide. That's not going to be on the test. Okay, so try to focus on what actually is covered and use that as your basis to review all the material. Okay, any questions about the test before we start? Yes. Can you use 2 pages? You can write on either side. Is that what you're asking? No, just bring one. It gets complicated because then we have to make sure nothing is written on the back or anything like that. Okay, one sheet. You can put anything you want on either side of it. Okay, and handwrite it. Don't type anything. Okay. Any other questions? All right. So let's start. Today we are going to start a new topic, which is leader election. I will conclude the discussion of distributed snapshots from before the break. There was something that we didn't cover, which is termination detection. Then we'll talk about leader election, and then we'll talk about distributed locking, which is mutual exclusion. Right? Okay. So all right. So termination detection. So what is this problem of termination detection? So assume that you have a distributed system of n processes, and these processes are performing some computation like simulations. Okay? And these processes need to figure out collectively whether the computation has finished so that the processes can quit. Okay? So the question is, how does a process know whether the computation as a whole has finished or not? Okay? So there are a very simple approach to doing this, which is an algorithm that is very similar to the distributed snapshot algorithm. In fact, you can piggyback it on top of distributed snapshot. As you're taking a snapshot, you can also ask the question saying, take a snapshot and figure out if the computation as a whole has finished so that the processes can then terminate, okay, terminate themselves. So the way you are going to do this is when you send out your messages as part of distributed snapshot, you are going to essentially send additional markers. These additional markers, these are not part of the distributed snapshot itself. They're additional markers that are used to indicate whether the computation has finished or not. Okay, so there are 2 types of markers: a done marker and a continue marker. Okay? A done marker basically says that this process has finished all of its work and it has no pending messages. Okay? A pending message means it has not finished work because there are new requests that are coming in and they need to be processed. But if there are no requests to be processed, all the computation has finished, there is no more messages that are coming in, and that process can send a done. Okay? So essentially, you wait for all of your neighbors to send you a marker. Okay? All your neighbors send you done marker, which means your successors of node Q send you a done marker. Q has not received any message since it checkpointed its state. Then it's going to essentially send a done, saying I'm done, my successors are done. So it will tell its predecessors is done. Otherwise, it will send a continue. Continue means that at least that process or something in its successor nodes have not finished some computation. Okay? So these messages are going to flow back all the way to the process that initiated the snapshot, and either that process is going to get done from all of its neighbor, or at least one of them will say continue. If any process says continue, that means the computation is not finished, so processes cannot terminate themselves. They need to keep running. But if everybody says done, then as part of the distributed snapshot, you can also say that the computation is finished and terminate the computation. Okay? So this is an extension to the distributed snapshot algorithm that we had spoken about last time. It's simply adding a feature which says take a snapshot and also figure out if the computation is finished, or does it still need to perform additional work before all of the messages are processed and the work is done. Okay? Any questions about this before we move on to the next topic, which is going to be leader election? Okay, the question is, what is the benefit of termination detection, or what's the benefit of distributed snapshot? Which of the two are you asking about? Okay, question is, what is the benefit of termination detection over distributed snapshot? So this is just extending the distributed snapshot algorithm. It's not an alternative, right? So you're still taking snapshots regularly, but as part of taking the snapshots, you're also querying all the processes in the network, whether they have finished their work or are they still computing something. That's all. So it's basically, if you can see this, it's just a query in through the network. It's asking whether the computation is finished. If everybody says they're finished, then the processes can quit, because the processes are independent processes, right? So they need to figure out whether they need to keep running or finish, right? So this allows them to figure that out. Okay. All right. So now we'll talk about election algorithms. So this is a different topic. Okay. So here, the goal of this election algorithms that we are going to look at is to choose a coordinator. Okay. So in processes, okay, you want to pick a leader. This is why it's called a leader election algorithm. And the leader can perform some task. What that task is not directly relevant to the election algorithm itself, but you can think of many things we have looked at so far. So in clock synchronization, we had a coordinator process, right? In many scheduling algorithms, we have a coordinator process. So rather than designating that coordinator statically, okay, you can pick it on the fly. You can run a leader election algorithm so that that process that becomes a coordinator gets chosen on the fly. And the advantage of leader election algorithm is if the coordinator dies, okay, the election algorithm will pick a new one. So you don't need to figure out, if you pick a static node to act as the coordinator, what happens to the system if the coordinator dies. Right? So all of these election algorithms are going to dynamically choose a leader, and also have built-in properties that allow them to detect a failed process, okay, and then rather elect a new leader. Okay? And we have already seen picking a master in the Berkeley algorithm and many other places where we need this coordinate. So these are the types of algorithms we are going to look at today. Will allow us to pick a leader. We'll see several algorithms, starting with Bully and then Ring and several others. Okay, so let's start with the Bully algorithm. It's a fairly straightforward algorithm. Okay, so here we'll assume there are n processes, and these processes have a numeric ID. Each of them is numbered, okay, 1 through n, or 0 through n minus 1. Okay. We'll assume that the processes know the IDs and the IP addresses of other processes. So every process knows the IDs and the IP addresses of other processes in the network. Okay. For very large systems, this is not a practical assumption, but let's assume the system is small enough that we can make this assumption. Okay? We'll assume connection is reliable, which is, let's say we use TCP. Okay? And the goal of the algorithm in this case is that you are going to simply choose the process with the highest ID as the current leader. Okay? Of all the processes that are still alive in the network, you want to figure out what's the process with the highest ID that's currently still alive, and we'll designate that as the leader. Okay? There could be many different criteria for picking a leader. This one is simply saying pick one with the highest ID. You could have said pick the node with the least load and make that the leader. Okay? Or you could have said pick the node with the most amount of CPU to be the leader. There could be any kinds of criteria. Here we are simply going to use the process ID, okay, as the criteria for choosing the leader. Okay? So the bully algorithm is a recursive algorithm. Okay? The way it's going to essentially work is as follows. Okay? Any process in the network can initiate the algorithm. So for example, let's say some process has not heard from the current coordinator. Okay? It can decide that the coordinator seems to have stopped responding, so start an election. Okay? So it's basically going to initiate the election, and then the election is going to recursively propagate through the network until there is a winner for the leader. Okay? And so I'll show you how that works. But the point that you want to note here is that the election algorithm needs to provide a consistent result. Okay? What does consistent result mean? It basically means that even if multiple nodes start election algorithm simultaneously, you always end up picking the node with the highest ID. Shouldn't be that two nodes detect the failure of the leader more or less at the same time, because we said any process can start an election. So both of those nodes might start an election to choose a new leader. Those elections should give a consistent result, which is the same node with the highest ID. They shouldn't give you two different results. That is going to cause some problems. Okay? So let's see how this is going to work. Okay. So here is a picture. So I'm going to first explain this with a picture, and then we'll see how this works. So here, let's say there are processes numbered from 0 through 7, okay, that are part of your distributed system. 7 was the previous coordinator. It's failed. Okay? So it's now gone. At some point, 4 is going to detect that it's not heard from 7 in a while. Okay? And say, let's start an election. Okay? So the way it's going to start the election is it's going to send election messages to all processes that have IDs higher than itself. Okay? Because the goal is to pick the highest ID node that's still alive. Okay? So it's going to basically send these election messages. So you'll see that 4 sends the election message to 5, 6, also sends to 7, but 7 has not responded. Okay? Now, when a higher ID process receives an election message, okay, it's going to send an OK message back to whoever sent it the message. So you will see 5 and 6 receive that election message. They send an OK message to 4. Okay? OK message essentially tells that node that there is at least one higher ID process that's still alive. So they will now figure out recursively who should be the leader. Okay? And that node should drop out of the election. Okay? So these two OK messages go back to 4. So 4 knows that there are some higher ID processes in the network, and it drops out of the election. Okay? And 5 and 6 are going to recursively do the same thing. Okay? So 5 is going to send an election message to 6 and 7. Okay? 6 will also run an election message by sending it to 7. The goal is to keep probing to see which is the highest ID process. Okay? So what will happen is 6 is going to send an OK back to 5. So 5 will drop out, and then 6 does not hear from 7. Okay? So 6 is going to declare itself the leader, and it's going to send a coordinate, I am the new coordinator message to all the process. So it's declaring itself as the new leader. Is that clear? Okay. So this algorithm is called the bully algorithm. Okay. And you can see why. Essentially, higher ID processes are essentially causing the lower ID processes to drop out. It's like bullying lower ID processes to drop out. And then you're recursively performing election until there is only one node left that is the highest ID process, and it becomes the leader. Okay. Any questions on this? Yes. You're saying if node 4 knows which processes are alive? Is that your question? Okay, question is, why is 4 probing all higher ID processes? Why is it not sending a message to 6 and waiting, right? So the point is that you don't know which processes are alive or not. 4 might only have heard from the coordinator. You don't know the state of other processes. So you always send message to all higher ID processes trying to figure out who is still actually active in the network, right? In addition to 7 other processes might have also crashed. And most processes will only be hearing from the coordinator. They don't directly communicate with other processes, which is why you probe all of the processes. Okay? What you're saying could be implemented as another election algorithm. I'm not saying it's wrong, but the goal of this algorithm is you probe recursively, and then eventually you end up with one process that wins the election. Okay? You could have said 7 has crashed, well, let's look for the next lower ID process, see if it's alive, and try to do something that way. That could have worked as well. Okay. Any question here? Yes. Okay, question is, how are the IDs assigned? In this case, IDs are assigned randomly. We are just assigning numbers 0 through n. Okay? But as you pointed out, there could be many policies to assign higher ID, node higher IDs. That could be based on resources. That's a good way to do it, saying, let's give higher IDs to processes which are more resources, because coordinators do more work. Okay? They need to have more resources to perform that extra work. Okay? So that could be a policy. As far as this algorithm is concerned, it assumes the nodes have already been given IDs. It's not asking how to give them IDs, but there could be many ways to do it. Okay? This assume random is the simplest one, but yes, you could do it based on load on the net, load on the nodes, resource availability on the nodes. All of these things can be thought of as policies. Okay? All right. So what do you think is the message overhead of this algorithm? There are n nodes. How many messages are exchanged before a leader is actually elected? Okay. So you should realize it's order n square, because you could have a case where the lowest ID process 0 starts an election, that triggers n messages, and rather n minus 1 come back, and then each of them basically keep going, and so you have order n square. Okay. So you will have 2n minus 1 plus 2n minus 2, and so on and so forth. So it's order n square is so it is not linear, but it's quadratic in complexity. Okay. You'll see one now that's going to be linear in its message complexity, but this one is quadratic message complexity. Is that clear? Okay. All right. So next one is ring based. So here we will also assume that processes have unique IDs, and we will take those IDs and order them in a logical ring. So again, if it's 0 through n, we'll make it a logical ring. It's not a physical ring, but we'll just assume that it's a logical ring. In this case, each process only needs to know its neighbors. In the previous case, you needed to know everyone's IP, because you have to send potentially a message to all of the other nodes. In this case, each node, because you are a ring topology, each node only needs to know its left neighbor and right neighbor. You don't need to know the identities of all the nodes in the network. Okay? So again, the goal is to pick the process with the highest ID as the leader. Okay? So we'll do the same thing as before. Any node can start an election. Okay? But in this case, the election message is going to propagate through the ring, and all that you do when you get this election message is you add your ID to that election message and you send it to your neighbor. Okay? And so this message is going to circulate through the ring. Each message that has, each node that has received the message would have added its ID to the ring. So when the message comes back to the initiator, it has a list of all the nodes that are alive in the ring, and it's going to pick the highest ID one and declare it to be the leader. Okay. So here's a picture to show the same scenario as before, right? So 0 through 7 are the nodes. Okay. In this case, we just arrange them in a logical ring. Okay. 7 has crashed. Okay. So you see that 5 has initiated the election. You'll see 2 also detected the node failure of the coordinator and started the election. Okay. So 5 is going to add its ID and send that message to 6. 6 is going to piggyback its ID and send it to 0. It can't send it to 7. And then, so this is going to circulate, and then when it comes back to 5, all of the processes would have added their process IDs, and then 5 will have the list. Okay, it just scans through the list, picks the highest ID process, and then sends another message to the ring saying this is the new leader. Okay, and the message from 2 is going to end up with the same result. Okay, because you will essentially have this message going all the way and comes back to 2. It sees all the processes that are alive. It's going to again pick 6 as the new leader and send that around. Question.
6 go to 7 0.
Yes, that's a good question. I was going to ask that question, but yes. So how does 6 know how to send the message? Because it did some update and okay. So let me repeat what I was saying. So in a ring topology, and we'll see another example of a ring in a little bit, typically you only need to know who is your left neighbor and right neighbor. Okay? But any network can have failures, and then the ring needs to heal itself, because if this node fails, you'll now see that the ring is no longer a ring. Right? You basically cut the ring. It's basically just become a chain. So to essentially restore the ring, you have to have a ring restoration process where you have to have some protocol that allows the two nodes that are now separated because of the failed node to essentially attach themselves to one another. Okay? You can do that in many ways. You can send a message in the backward direction and figure out what was the other neighbor of 7, for example. Okay? Because 6 was communicating with 7. 6 doesn't know who its neighbor is. But if you send a message in the backward direction, you can then figure out that 0 was 7's neighbor and then get that and try to connect to itself. So there has to be some healing protocol to restore the ring. Okay? And once the healing protocol completes, then 6 will know that it has to essentially communicate with 0. Okay? But that's for any ring topology, that is basically something you have to add to ensure that when there are nodes that fail, you can still continue to operate as a ring. Otherwise, your ring will break. Okay? That's not part of excuse me, that's not part of the election algorithm that we have to worry about. Here, we just assume that when a node fails, the ring has essentially healed itself. Okay? We are just running the election algorithm on top of that. So we don't need to worry about it, but that's an additional detail that you do need to worry about in an actual ring implementation, independent of whether it's election algorithm or something else. Is that clear? Okay. All right. So complexity 2n minus 1, okay, because the message is going twice through the network. Okay, so it's linear in complexity as opposed to quadratic in the previous case. Okay, so essentially the worst case is that node with the lowest ID is going to initiate. It always triggers 2n minus 2 elections, and best case is n minus 2. Okay, so this is going to have lower overhead than the bully algorithm, okay, giving you similar results. All right. Okay. Yeah, the question is, will the ring algorithm take longer time because you are essentially passing messages sequentially? It will take more time, right? Because you are going to sequentially probe all the network. In the bully algorithm, you are probing nodes strictly higher than your ID, right? Here, all the nodes are probed because you are just sending it through the ring. So it is going to take, it has lower message complexity, but it will take longer because you are going to have, imagine you have 10,000 nodes. Right? In the ring, you will have to go have the message go through all of them. Okay? Whereas if you had a bully algorithm, okay, the worst case is when the lowest ID node starts the election. That triggers lots of messages. But the average case is when some node with some middle ID starts and only the higher ID nodes will get probed. So it will take less time as a result. Okay, the number of messages will be higher, but it might converge faster. Yes. Yes, in bully algorithm is recursive and you can send things in parallel. Here you are always going to do sequential, right? It has to circulate through the link. So it's linear. Any other questions? Yes.
Will the algorithm always resolve it? Always send an election message to the highest node, and then it will send an election and it won't get a response. So it will, after 2 time steps, think that it's.
So you are saying, will the bully algorithm get things done in 2 time steps because you will send a message to all higher ID processes, and then they will recursively start an election and then convert? That's your question, right? So in practice, that's true, but the amount of messages that get sent because you are recursively starting on the order of n-1 election, depending on who triggered it in parallel, right? That will take high message overhead, but it might converge faster. And whether it's 2 time step depends on whether all of them start all at once or they randomly start at slightly different times, is a different implementation detail. But yes, if they synchronously start election, it will converge in 2 time steps. Yes.
After 5, 6, if 0 is the next thing, it automatically means the 6 is the highest.
Yes. The question is there any benefit to having this go through the whole network? Because after 6, when it goes to 0, you know that 6 is basically the leader. You have chosen the leader for sure once you start encountering lower ID processes, but because the ring topology, it doesn't allow you to send messages out of order. So it's not like 0 can send back a thing U1 to 6. You have to still have it go through the ring in that order. It will still propagate through the ring, right? But that's what we said. You can only communicate with your right and left neighbor. Yes.
In the case where 7 and 3 are, how would that be?
If 7 and 3 are both down, how does the message go back to 6? Is that your question?
Yeah, how do we? Because now
right. Okay. Question is, what happens if there are multiple failures at the same time? Okay. So if there are multiple, I mean, this is all part of how to maintain a ring, okay, which is not really part of the election algorithm. But if you have a ring topology, the fundamental part of that ring topology is to maintain the ring when nodes fail, right? So there could be many approaches. I mean, I gave you one example. Another approach could be that another simple idea could be each node not only keeps its left and right neighbors, but also its left neighbors also, right? So 6 would not only keep track of 7, but it also keeps track of 0 and 4, so that if it left or right neighbor dies, it knows who to connect to, okay? And so on and so forth. You can come up with many approaches. You could say, what if both 6, 7, and 0 die? Maybe you can say, okay, you can keep 3 neighbors. Okay? You have to assume how many failures can occur simultaneously and decide how much information to keep. Okay? So you can always heal the ring in many different ways. Any other questions here? Is communication bidirectional? Can 0 communicate with 6? That depends on the ring. Yes, rings can be bidirectional. Here we are assuming unidirectional ring, which is why it's circulating in one direction. But yes, you can have messages go clockwise or anti-clockwise, or you can stop the message and send back if you don't need to have it go through. But this one is assuming a simple unidirectional ring. The ring is not able to heal, then the protocol will fail, because that's basically no longer a ring at that point. Yeah. So, but you assume that the ring is part of the network layer. We don't worry about it at a application layer. So election algorithms are essentially running as an application. You just assume that the network layer has figured out how to keep the ring as a ring, right? And then you just operate on top of it. But yes, if the ring fails, and we'll come back to that actually when we talk about locking, I'll talk more about that as well. All right. So that we talked about two techniques. Let's talk now about distributed synchronization, which is locking based approaches. So here we are going to now think about how do you implement a distributed lock. Okay? You all know what a lock is. You typically use a lock in a single process, right? Now assume that there is a set of n processes that are coordinating with one another or work interacting with one another, and there are some shared information, maybe their shared file or shared database, and they need to grab a lock. Now you will have these n processes together constructing a lock. Rather than the lock being part of one process, you want all of them to basically implement what we call a distributed lock. Okay, the question is, how will you implement mutual exclusion with multiple processes? Okay, we know how to do this for a single process. You probably used locks in your, not probably, you did use lock in your lab, where you use semaphore lock monitors. That was a single process, right? Here we have n processes, and so we are going to do this in a distributed system. Okay? I will show 4 different lock implementation. Some will use a centralized coordinator. We'll essentially elect a lock coordinator using an election algorithm, and then that coordinator will help us implement a lock. And then we'll have several distributed versions of these lock algorithms. Okay? So let's start with one example of why you need lock. Here is an example to show you why this might cause problems. So assume that you have 2 clients. There's an online store. Maybe the clients check if there is some item in stock, and then they both send a buy request to buy it. Right? So if there is no lock, you might essentially get an error because the first one will succeed, and the second request will come when the first request has already bought that, maybe the last item of that stock, and it will fail. Okay? So you want to ensure that the clients can essentially get a distributed lock so that only one of them can buy that item at any time. Okay? This is one simple example of why you need locking. There are many others that we can use as well. Okay? But let's now look at an example of how do you do this. Okay? So here is how we are going to implement a very simple centralized mutual exclusion. Okay, this is somewhat of a misnomer because we are implementing a distributed lock using a centralized coordinator, but leaving that aside for just a second, we'll assume that processes are numbered like before. Okay? One process is elected the coordinator, the lock coordinator. We know how to run election algorithm. You'll just use your election algorithm, elect a lock coordinator. Okay? And the goal now is that when you want to grab the lock, you will send your lock request and release request to the lock coordinator. Okay? So you'll basically, to grab a lock, you'll do lock acquire. Okay? You'll send lock acquire as a RPC message or some socket message to the lock coordinator. If the lock is free, okay, you will basically get success, so then you get the lock. Okay? The lock is in use, your request will be queued there, so you will be blocked waiting for the lock to be acquired. Okay? Except that now you are using network messages to do this rather than using a function call. Okay? So basically, the goal is the coordinator is going to receive these messages. Okay? Whenever it receives a request message, if the lock is available and the queue is empty, which means there's no other request before it, you grant the lock. Otherwise, you will queue the request. Okay? When the lock is released, you take the next request from the queue and grant the lock. Okay? Here's the picture that shows you how this is going to work. Okay? This picture has 4 processes, 0 through 3. Okay? We will elect the coordinator first. 3 becomes the coordinator. Okay, so initially the lock state is available. The queue is empty. There's no request on the lock. Okay, so when 1 makes the request, okay, it immediately gets the lock because it's now available. Okay, and then 2 makes a request. Okay, at this point the lock is in use, so this request is queued. Okay, it's not going to get any reply back from the coordinator, so 2 is blocked. Okay, similar to how lock acquire will block until the lock is free. Same thing. Okay, so your RPC message is not going to get you a response, so 2 is going to be blocked. And once releases the lock, okay, 2 is going to basically be given the lock through the OK message. Okay, is that clear? All right. So this looks very simple, but the problem comes when there are failures in the network. Okay? Because the distributed locking, although it seems very simple, is actually quite problematic because all kinds of things can fail. This is a distributed system. Okay? So let's take several examples. Okay? what things can fail. So let's say that one has grabbed the lock. Okay? At this point, the first step was one requested a lock and it got the lock. Okay? And let's say one crashes. Okay? It's holding the lock and the process is gone. The lock is never going to be released. Okay? So now any other process that requests the lock will block forever and your system will deadlock. Right? This is not something you will see in a normal process, because if something crashes, the whole process will crash. Here, parts of a system have crashed. Okay? Now you will basically not have the lock back. Okay? Or the coordinator might crash. Okay? Now you might choose a new coordinator. You can run leader election and choose a new coordinator. But you need to restore the state of the lock. Okay? You need to know what was the state. Was it granted to someone? Was there a queue with multiple requests? You need to figure that out. Okay? How do you do that? Of course, you have to log that state to disk. Otherwise, you will not know what it is, and so on. So coordinator crashes, process crashes, all of that can complicate this implementation. This looks fairly straightforward in this example, but implementing it is quite complicated, because you have to handle failures carefully. Otherwise, you will not get mutual exclusion, or you will get a deadlock. Okay? So this is basically where all of these things get more complicated. Okay? So essentially, the properties of this algorithm is, excuse me, so using a centralized locks to implement blocking calls. It's very simple. Okay? It's granting locks in the order in which they're received. So it's fair. Okay? It uses 3 messages, okay, to essentially grant, release, and request. So it's fairly straightforward in his message overhead. Shortcomings are it's a single point of failure, which means if the coordinator crashes, there's a problem. If any process crashes, you're a deadlock. Okay? So these are all things that you will need to deal with when you actually make a proper implementation. Okay? Any questions here? I'm not going to describe lots of details of how do you deal with the failure cases. You just need to know that you have to deal with them in some reasonable way. All right? Okay? So that's our simplest approach. Now let's try to make that more complicated by saying, let's remove the need for a centralized coordinator. But if the coordinator crashes, then we have a problem. Okay? So we'll use a decentralized approach, where rather than one coordinator, we have many coordinators, right? And we'll use voting between coordinators. Right? So we basically relax the assumption that there's a single coordinator. You have many coordinators in the network. They're all tracking the state of the lock. Okay? And when you ask for a lock, these coordinators are going to decide what to do and vote. Okay? And majority vote wins, which means that if some coordinators are down, the other coordinators can still figure out what to do. And so long as they're in a majority, you are confident that the lock state is correct. If you're a minority, you don't know whether the lock state is correct, with a majority who have failed might have some other state of the lock. But so long as the majority of the coordinators that you have designated are still up, they can track the state of the lock. Is it free? Are there requests queued, and so on? So we are essentially going to use majority voting to figure out, and then the coordinators can then return back the result of whatever the request is. Okay? So this essentially is approach where you have many coordinators. Okay? These coordinators, like the centralized case, are going to track the state of the lock. Okay? Whenever a lock request comes in, okay, they will figure out, each coordinator figures out what the response is to that request, similar to the centralized algorithm, and they will vote. Okay? And so long as there's a majority vote, that majority vote is then going to determine what is the next step. Should the request block? Should the lock be granted? And so on and so forth. Okay? So this is essentially going to reduce the problem of what happens if the coordinator crashes, because we will essentially not have that problem by having many coordinators. Okay? Increasing the complexity of the algorithm, but it gives you a little more resilience to failures of coordinator. Okay? This does not handle client failures. Okay? Now we basically dealt with coordinator failures, but the problem of a client crash is still there. A client holding the lock may simply die and never release the lock. Your system will still deadlock. That problem we have not solved. Okay? But at least we solved the coordinator problem. Okay? So as you can see, these are quite complicated when you try to deal with all kinds of failures that can occur in the network. Okay, so this is a decentralized approach. Okay, I'll show you two more approaches. Okay, here is another one, okay, which is called the Ricart and Agarwala algorithm. Okay, this one uses Lampert's clocks that we looked at several classes ago. Okay, so the idea here is that every time a process is going to request a lock, it's going to attach the Lampert's time clock value to that request. Okay, and what happens is it's going to then send to enter a critical section. You essentially increment your local Lampert's clock value, and you send a request message with that your Lampert's clock to all other processes. Okay, so you are basically saying I am request K, my Lampert's clock value is TSK, okay, and I need the lock. So that's the request message. It goes to all processes. There's no coordinators here. Okay, so you send this to all processes in the network, and you have to wait for a reply from every other process, which a reply simply says go ahead, you can have the lock. You have to wait for a reply from every other process before you can enter the critical section. Okay, until you have received an OK from every other process, you cannot, you're blocked. Okay. Now when a process receives a request message, process J receives a request message from another process, it can do one of two things. Okay. If it does not need the lock, if there's no contention, it's going to send a reply. Reply means go ahead. I don't need the lock. If you need the lock, go ahead. Okay, that's what a reply means. Now, if it's already in the critical section, it's going to not send any reply at all. It's going to say, I am already holding the lock, so I will wait until my lock is done before I send a reply message. Okay? And the third one is it is also trying to enter the critical section, which means that it has itself sent request messages. In this case, you are going to compare the Lampert's clock values to see which of these has a lower Lampert's clock timestamp, and the one with the lower timestamp will win because that's the one that made the request first. Right? So essentially, if you want to enter, you compare your timestamp with the one with K, and you send a reply value if the one from K has lower, which means that it made the request first. Okay? So three cases. One is there's no contention, so you send reply. If you're already holding the lock, you wait until the lock is done, then you send the reply. And the third case is when this process that received that request from the other process is also trying to contend for the lock, and then the one with the lower timestamp wins. Is that clear? We just used Lampert's clocks to figure out how to do locking. Okay? No coordinators in this case. Right? You are asking all other processes. Okay? So it's good and bad. The good part is there's no coordinator. You don't have to deal with coordinator crashes. But the bad is every process in the network has to participate in locking, whether it wants the lock or not. Any random process needs the lock, you have to essentially participate in the protocol, send reply messages, and so on. Okay? And you have to get reply messages from all other processes to proceed, which means that, again, if you have any of the process that has crashed, you will not get a reply message from them, right? Because the process is crashed. And then you cannot grab the lock. Right? So essentially, we went from one point of failure to n points of failure, which means that any process that crashes in the network, the entire locking algorithm fails. Okay? In the other one, at least if the coordinator failed, the lock algorithm failed. Here, any process crashes, no one can grab the lock. Right? So it's good and bad. The good is fully distributed or decentralized. Bad is there are n points of failure. Okay? This is one of the few cases where you may go from a centralized algorithm to a decentralized algorithm, and the failure property actually gets worse. Normally, when you remove things that are centralized, you get better resilience, you get better failure resilience properties. Here, you actually made things worse. So this is just an example to show you not every decentralized algorithm is always better than a centralized algorithm. Okay? Generally, they are, but here is a counter example where this is not the case. Okay? So this one uses clock values, and there is one more that I will talk about, which is our token ring algorithm. Okay? So this gets us back to a ring-based topology, and we'll see how this can be used to implement a locking algorithm. Okay? So we'll assume here that we have processes that are numbered, okay, and they are part of a network. Okay, this is the physical network, but because they are logical ring, then the logical topology looks like that, where 0 can only talk to essentially 1 and 7 and so on. Okay, so you can only talk to your left neighbor and right neighbor for the locking protocol. Okay, for other messages, any process can directly communicate with any other process because it's not necessarily a physical ring. Okay, so here is how we are going to make the lock protocol. We'll construct a special message called a token. Okay, and we'll get the token to circulate through the network. Okay, so to grab the lock, you don't do anything. You just wait for the token to come to you. Okay, and once the token message comes to you, you hold the token message, and when you're holding the token message, you have the lock. Okay, and then you can do whatever you need to do. And then once you're done with the lock, you pass the token message to your next neighbor. Okay, so the token is going to keep circulating in the ring. Okay, and so to grab the lock, you just wait for the token to come to you. Okay, and when the token comes, you know you have the lock, and then you can essentially do whatever you need to do in your critical section, and then pass the token to the next process. Is that clear? Very simple technique. Okay, no acquire, no release, no nothing. You just construct a special message that's just going to keep hopping through the network. Okay, so it will be at 7. Once 7 is done, it'll send it to 0. If 0 doesn't need the lock, it will immediately give it to its next neighbor. If it needs the lock, it was waiting, then it'll do whatever it needs to do. And when it's time to release the lock, then it sends to the next neighbor and so on. So this token message just keeps circulating. Okay, and holding the token message, there's only one token in the network. So holding the token guarantees to you that you actually hold the lock. Is that clear? Okay, so this is essentially called the token ring algorithm. Right? Now, the interesting part about this algorithm is, although this is a simple locking protocol, this was also the basis for a local area network technology that no longer exists, but that was prevalent about 20, 30 years ago. Okay? In the 90s, there were two LAN technologies. There was something called Ethernet, which is now, of course, the one that eventually won and became commonplace. But there was another one called token ring. Okay? So in those days, when you bought a computer, you had to decide, do you want an Ethernet card in your machine or a token ring card? And that depended on whatever technology your organization had chosen. If you are a token ring organization, you have to get a token ring based card. Otherwise, you have to get an Ethernet card. Okay? And the idea in the token ring was basically all the PCs in the network essentially were arranged in a logical ring. Okay? And the reason you needed the lock was the computer could send a message to any other machine in the network only if it held the lock. Okay? Because if two machines try to communicate at the same time, those packets would collide. Okay? And they would corrupt each other. Okay? So the idea was you have to essentially have a lock on the network for you to transmit to some other node. Okay? And this token ring, this token packet essentially gave you lock over the network. And if you had the lock, you know no one else can transmit. So when you transmit, you know it's safe to send and nobody else can send at the same time. Okay? So that was the idea. Okay? If you know anything about Ethernet, you will know that in Ethernet, you basically use a randomized algorithm. Okay? You essentially transmit, and if two machines transmit at the same time, you have something called a collision, because the packets basically collide and you don't transmit successfully. Then you have a randomized backoff, where you wait for different amounts of time and retry. Okay? So there may be many attempts in Ethernet before packet is successfully transmitted, because multiple nodes are trying to send at the same time. And whenever there's a collision, you have a problem. Okay? Token ring tried to solve that by saying you have to actually have a lock. You cannot just transmit whenever you want. You have to grab the lock and only then transmit. So it's always clean. There's never going to be a case where there's going to be collision in the network. Okay? Okay. So still transmitting from here. Okay, let me see if there's any problem. Okay. All right. So, so that was the basis for token ring algorithm, but there are still problems in token ring. Okay? So let's say that there is a node holding the token, okay? And that node crashes. Okay? So the token has disappeared. So now what do we do? Right? There's not going to be no more token that's circulating through the network. This is a LAN technology, then there's no token, so you cannot transmit. Fundamentally, all your communication will stop. Right? Or if you are using this for locking, you will wait forever, you will never grab the lock. Right? So there has to be a way to detect token failures, okay, and regenerate the token. Right? Now in token ring, the network protocol, this was straightforward. Okay? But in the regular, more general case of actually making this a locking protocol is not straightforward. Let me explain why this is the case. Okay? In the network-based token ring protocol, when you hold the token, you had a limited amount of time for which you could hold it. You couldn't hold it forever. Let's say you are given, if you have the token, you can hold it for 100 millisecond max. Okay? After 100 millisecond, even if you have more data to transmit, for fairness, you have to send the token to the next node so that everybody gets a fair shot and you're not waiting for long periods of time because somebody decided to transmit a 1 gigabyte file and then nobody else can transmit because you're holding the token. So you could hold the token for a limited amount of time. Okay, so let's say it's 100 milliseconds. Okay, now if it's 100 milliseconds and it's now 8 nodes in the network, it's if you just do the math, you will know every 800 milliseconds you should have the token max, and you can get it faster if somebody doesn't use their entire slot. Right? So you can detect a token failure because you have to receive the token in a bounded amount of time, and that time is known. It's dependent on the size of the ring and the max amount of time you actually hold the token. Right? So if you don't see the token after that amount of time, you know the token is lost. Okay? You also know probably that the ring has failed. Okay? Then you have to do the ring healing that I talked about and regenerate the token. Okay? And you have to do this in a proper way that your 2 nodes don't regenerate the token. So you have to designate some node to regenerate the token and so on. Okay? So in token ring protocol, the network protocol, it was straightforward. But let's just say you're using this in a distributed system. We don't impose any time limit on how much time you can hold the lock for. Right? You can, once you do lock acquire, there's no such thing that you have to give it up in 100 milliseconds. You can hold it as a process for as long as you need to. Right? So there is no bound in the general case. Right? So in the general case, the token might be lost and you will never detect that it has lost because you don't know if it's actually lost or is there some process that's holding the lock for an excessively long time in some very long critical section. You cannot distinguish between these two cases. Right? So you can't simply say the token hasn't arrived, it's been 5 minutes, let's just regenerate the token. And if there's a process that actually held the lock for 5 minutes, it will release the token. Now you have 2 tokens in the network. Right? That's also bad because 2 tokens don't work. You can only have 1 token in the network. Right? So handling token loss is non-trivial in the general case, but it's more straightforward in the network case. Okay? So that's your token ring protocol for locking, but it actually has its origins in networking technologies. Okay? This is back in the days where Ethernet and token ring used to compete with one another. Eventually, Ethernet won, and token ring just went away. Okay? Any questions here? The audio back? Yeah. All right. So very quickly, there is 4 algorithms we looked at. There are some properties here in terms of how many messages you need to deal with and so on. We didn't analyze this, and this is really not the important part about which one has more overhead and so on. The real problem is all of these algorithms are basically problematic from handling crashes. Okay? None of them are perfect. Every one of them has some flaws in terms of if the coordinator crashes, there is a problem. If a process that holds the lock crashes, there's a problem. There could be a starvation. Okay? In the Rickard and Agarwal, any process crashes can basically freeze the entire algorithm. The token ring, lost token can cause a problem. Right? So what this is trying to tell you is distributed locking. Okay? Although we studied a bunch of these protocols, it's not trivial to implement in practice because handling failures is where pretty much all of them have their weak spot. They all have some problem or the other. and you can make some assumptions to resolve them, but it's not trivial in the general case in all of them. Right? So this is why it's complicated to implement. You don't see general purpose implementations of it, although there are systems, and I'll show you one that actually implement locking type algorithms in the distributed case. Okay. All right. So let's do a very quick case study, and then we will wrap up for the day. So here is an example of a system that Google built. It's called the Chubby locking service, where they implemented a distributed locking system. Right? So the idea here was, this is a locking protocol, and any of the applications in the Google's network, when they needed a lock, you can go to Chubby, and Chubby can be the coordinator of the lock. You can instantiate a new lock, you can acquire a lock, release a lock, and the locking service will implement locking protocol for you. Okay, so it's designed for coarse-grained locking. It is not a fine-grained locking protocol. Okay, it uses file systems abstractions for holding lock. Okay, so essentially, you have a Chubby cell, which is a set of 5 machines that support locking requests from about 10,000 servers. So for every 10,000 servers, they made 5 servers as locking servers that implemented the Chubby protocol. And one of those servers was actually kept in a different data centers, so that even if the entire data center failed, all the states of active locks don't go away. Right? Because I said coordinator crashes, you don't know what the state of the lock. So there are 5 coordinators. Right? One of them is actually kept outside, so that even 4 of them go away, entire data center goes down, you will still have some other machine somewhere else that can figure out what's going to happen. Right? So, and they essentially used a file system interface. So they kept the state of locks as files on the file system. They have a locking protocol, but the state was also always preserved on disk, so that even if the memory state goes away, the disk state actually preserves the state of the lock, and you can reconstruct it. Okay? And so they implemented this Chubby locking service. It's widely used in the Google system. They use it to essentially perform leader election. They use it to do coarse-grained synchronization, where you can hold locks for hours or days. Right? So you can see that it's really coarse-grained. You're not getting locks for second or millisecond time scale. You can grab a lock and do some computation for 1 hour or 10 hours or several days at a time. So it is coarse-grained in that regard. It's not meant for the kinds of locks you implement in your code, which are more fine-grained locks. Okay? So here's a picture of how this works. So you will see that this is essentially the 5 servers of a Chubby cells. Okay, you essentially have the Chubby library that you can but incorporate in any application. And then you can essentially use the Chubby service lock acquire and lock release. Those requests go to the master. It can create new locks, can grant locks, and so on. It uses RPCs, and specifically gRPCs, for communication between the application and the locking service, which are all the coordinators. Right? So this is an example of how some of these ideas are now used in large-scale distributed system. Okay? So of course, you can have some of those Chubby masters fail, and then you can use leader election to add new masters, so that you always have 5 of this node if some of them disappear, and so on. So those techniques are also part of the Chubby locking service. Okay? So it's just a very quick insight into how some of the ideas we talked about are implemented in larger systems. Okay? Any questions here? Yes.
So what are like modern databases?
Okay. Questions: what do modern databases use to deal with these issues? So there are 2 ways to think about what you just asked. Databases are still by and large single machine databases. You can have distributed databases, clustered databases, leave them aside, because we will come to distributed transactions soon. But you take a modern database, even though it may be a large database, it's single machine. Right? Single machine, there's no problem. All the locks can be implemented on that machine. Okay? Locks are extensively used in databases. They are extensively used in transactions. We'll start looking at some of these techniques very soon. Okay? But they don't do this distributed thing, right? Because that's much more complicated. So they basically are centralized. all the locking is within the database. There's one database process, so it's much more straightforward. There's extensive use of locking, but it's more straightforward. It's no different than you using locks in a Python or a Java program. You just think of database as some large program that's using locking internally. Okay. Now, having said that, there are of course distributed databases, right? So there the database spans multiple machines, right? So when you're distributed databases, you do need to implement some notions of this. But rather than implementing this at a locking level, databases do this at a transaction level. So they will implement these types of properties using this concept of a transaction. And we will look at distributed transaction in a lecture or two. Probably it's the next lecture or maybe the lecture after that. And you will see how distributed transactions can be implemented, right? So it's basically in databases, you use a higher level abstraction. You don't deal with locks, you deal with transactions, and transactions will internally use locks. Okay. Any other questions here? Okay. So I think I'm done with today's lecture. So we'll stop here and continue next time.